Hello, everyone. This is Arvin Sahami, and I'll be talking about work with Professor Nick Harvey about explicit orthogonal arrays and universal hashing with arbitrary parameters. So the plan for this video is that I'm first going to introduce you to the main problem. Then I'm going to talk about a key ingredient for our constructions, which is something called the reassigning procedure. Then I'm going to give you a concrete construction, which is based on read-solvent codes, and we will then hunt for primes. Next, I'll tell you about how we're going to get our final construction, which is going to use AG codes. Okay, so what are orthogonal arrays? Orthogonal arrays were introduced by Rao in 1947. And they originated from factorial designs in statistics. I should mention that Professor Rao unfortunately passed away very recently in the August of 2023. So as you can see, orthogonal arrays have a book dedicated to them by Hedayat et al. And so, which shows that they're well studied. So let's define an orthogonal array. So in the context of statistical experiment design, you have m variables or features, and you also have n different levels. And then you want to design experiments that you want them to be t-wise fair. What does that mean? For our case, this means that among each of these t variables, any of the n to the t possible combinations appears equally often. Now, our goal is to do as few experiments as possible while satisfying this criteria. So then a trivial approach is, of course, to try all of the n to the n possible combinations, but and that's going to work for any t. However, that's not great because n to the m is very big. Okay, so let's give an example of what an orthogonal array is going to look like. So an orthogonal array is a matrix which the features are the columns. So here I have 11 columns. My m is 11, and my levels are just 2, 0 or 1. So n is 2. And in this example, we have a 2y sphere orthogonal array. This parameter t represents the strength of the orthogonal array. And so in this example, we're going to bake cakes. And my features are stuff like, oh, do I put butter in it, or do I put sugar in it, etc. or not? And I'm going to bake 12 cakes. Okay, so then what does it mean to be 2y fair? Well, it means if I pick any two columns, so here, for instance, I've picked the second and fifth, the number of appearances of 0 zeros will be the same as the number of 0 ones and 1 zeros and 1 1. So they all appear 3 times in this case. Okay. Now I'm going to jump into another notion which might be more familiar, which is that of t-independent hash families. So generally speaking, a hash function refers to a function whose output has random properties. And a t-independent family is a more specific notion, which is a multiset, big H, of a bunch of mappings of a domain, like 1 through m, to a codomain 1 through n, which satisfies the following property. If you pick any t distinct entries, x sub 1 through x sub t and 1 through m. And when you pick a function h, small h in big H uniformly at random, then the t random variables h of x sub 1 to h of x sub t are going to be IID in and uniform in 1 through n. So this is a well-studied notion and has various applications. For instance, if you want hash functions that have provable guarantees, or for de-randomization, for constructing hash tables in areas such as complexity theory, and etc. Okay. And here's an example of a t-independent family when t is 2, and the codomain is binary, so n is 2, and the domain has size 11, let's say, so m is 11, and the size of the family is 12. And so you can see that I just took those cakes and sold them to you as hash functions. And in fact, you can, of course, make this more rigorous, as was made by Stinson in 1993. So t-independent families and an orthogonal array of strength t are exactly the same object via a trivial correspondence where you just see the rows of your orthogonal array as a function in the t-independent family. So let's just quickly go over some of the analogous features. So in this video, I'll be referring to the independency parameter of the t-independent family, which corresponds to the strength of the orthogonal array by t. The number of columns in the orthogonal array is going to be denoted by m, which corresponds to the domain size of the t-independent family. The number of levels in the orthogonal array will be denoted by n, and that will be the codomain size of the t-independent family. And the number of rows is denoted by s, which is, of course, the number of functions in the family. I'll be abusing notation for convenience, so I'll treat the matrix of an orthogonal array both as a matrix and as, a multiset, as a family of functions. Okay, so what's our goal? For the purpose of this video, suppose that you're given some t, m, and n, and you're asked to find an orthogonal array with as few as many rows as possible. So how small can S be given some arbitrary t, m, and n? Oh, I should mention that for the definition to make sense, you're gonna require that t is at most n. Okay. So let us discuss some bounds for S. So Rao, who defined orthogonal arrays, also showed a lower bound on the number of rows of an orthogonal array with parameters m, n, and t, so with m columns, n levels, and strength t. He showed that the number of rows is at least c times m over t times n to the power of t over 2 for some universal constant c. Okay. And in fact, there are constructions based on error correcting codes that achieve S, for which the S is a polynomial in this Rao lower bound. However, these constructions only work when n is a prime power. And so a very natural question is to ask, well, what happens when n is not a prime power? And a result in this direction is a result of Kupperberg, Lovett, and Pellet, which is non-existential. And it says that for any arbitrary parameters m, n, and t, well, with t being at most m, you can there exists a orthogonal array with s rows where s is a polynomial in this Rao lower bound. Okay, so the problem with this KLP approach is that it's probabilistic, but with a tiny success probability, which means that it doesn't give you any efficient randomized algorithm to construct the object. And so it is an open problem to either find a deterministic or a randomized algorithm which works with high probability to construct these objects. Okay, and this is the problem that we're gonna focus on in this video. And the following is our main result. Namely, we can construct the same, we can construct orthogonal arrays that achieve this number of rows being a polynomial in the lower bound via a deterministic explicit construction. So for any arbitrary parameters m and n t, well, again, with m being at most t, we will construct an orthogonal array whose number of rows is a polynomial in the Rao lower bound. And we furthermore can build the whole thing in polynomial time in its size, so in poly-SM time. Of course, our proof will be completely different from the Kuperberg, Lopez, and Pellet result. Okay, so in the rest of this video, will be trying to describe how our construction will look like. But before that, let me mention some of the basic constructions that you can do. So a trivial thing is to take all the n to the n possible things, n to the n possible combinations, and of course, that's not great because n to the m is very large. So what else can you do? A smarter thing is this polynomial construction due to Bush in 1952, and it's essentially the same as Reed-Solomon codes. This was rediscovered by Wegman and Carter in the context of hash functions. So what is this construction? It also requires n to be a prime power. So so this construction also requires the number of levels to be a prime power. So suppose t is at most m and m is at most n. Well, of course, t is always at most m, but this construction does require m to be at most n, and that's a significant thing about it. Then if you just look at all the polynomials with coefficients in the prime field of size n, and whose degree is less than t, well, they're p to the t, which is they're n to the t, such polynomials, then this is going to give you a t-independent family, same thing as a orthogonal array of strength t, as we mentioned before. Okay, and you can show this via a simple Lagrange interpolation argument. And so this is actually a subset of constructions coming from codes. So error correcting codes are a main source for constructing orthogonal arrays because of the following connection, that if C is some code of length m and dimension k, distance t over a alphabet size of p, then the dual code C perp is an orthogonal array with p to the m minus k rows. The length is, or the number of columns, if you will, is m. The size of the number of levels is p, and the strength is t minus 1. So the distance sort of corresponds to the strength of the orthogonal array. Okay, and this is great because now we can avoid the trouble of m being at most n, but this construction still requires n to be a prime power. Okay, so now I'm gonna tell you about our procedure. the reassigning procedure, which is a main ingredient for a result. So the general theme is going to be that we're gonna start from some orthogonal array which is given to us, and then we're gonna build up a new orthogonal array based on the old one. Now, the goal is that this new orthogonal array has a level size which is one less than that of the original one, while it has the same number of columns and the same strength. We also want the size to be reasonable, so we would want the number of rows in this new thing to be not much more than whatever we started with. So if we start with an orthogonal array m sub big N, which has levels in 1 through n, we want to build this new orthogonal array m sub big N minus 1, which has also m columns and strength t, but is over levels of 1 through big N minus 1. So a very natural idea to do this is to just reassign those entries of your orthogonal array that are equal to n. So somehow get rid of them. So I'm going to describe what the procedure is by going through this example. So let's begin, which is the original level size be 7, and suppose you have 8 columns, and let t be 2 be the strength of this given orthogonal array. So here's a picture of a part of it, and I'm gonna take some row, an arbitrary row, and I'm gonna do the following procedure on it. So I'm gonna look at all these 7s, and then I somehow want to change them to entries in 1 through 6. Now I would want to do this in a fair way, so how about doing it in random? So if you assign a random variable to each of these, maybe that's sort of fair, and so maybe that would work, but doesn't really make sense because you would want to assign a single number to each of these entries, not a random variable. So a way to put numbers there would be to just take all the 6 to the 3 in this case combinations. And so each of these rows, this single row R would produce an ensemble of rows. And it turns out that to keep the t independentness, or keep the strength to be t, you would have to repeat these ensembles in your new orthogonal array the right number of times. And this right number of times it can be easily found to be inversely proportional to the number of rows in each ensemble. So the general idea is that each row should produce the same number of rows in the new orthogonal array. Then I'm going to put all these ensembles together to get a huge matrix, which will be my new orthogonal array. And so while doing this procedure, it turns out that each row produces exactly a big N minus 1 to the tau new rows, where tau is the maximum number of letter n's appearing among the rows of the original orthogonal array. So here's our result. So if you start with some orthogonal array which has m columns and its levels are in 1 through big N, then you can construct this new orthogonal array which has the same strength t, and the number of rows is going to blow up by this factor of n minus 1 to the tau, while reducing the number of levels by 1. Okay, so that's one step. here's the second trivial step that suppose your target level size is small n, and this small n happens to divide big N minus 1. Then you can do a trivial thing, which is, well, you're gonna take your orthogonal array with big N minus 1 levels, and then you're just gonna mod out all the entries modulo small n. So you can also see that this operation will also preserve the independence, and therefore you put these two together, you'll get the corollary at the bottom that if you have some small n that divides big N minus 1, and you start from some orthogonal array over big N levels, then you can actually construct a new orthogonal array which has small n levels, the same strength T, and the same number of columns M. However, the number of rows is blown up by this factor of n minus 1 to the tau. Tau is as defined above, is the maximum number of letter n's appearing among rows of the original orthogonal array. Okay, so I described a procedure which started with some given orthogonal array and produced a new one, but I haven't really given you a way to efficiently construct orthogonal arrays from scratch. So now I'm gonna go ahead and give you a concrete construction, which is as follows. So let's begin to be a prime power p, which satisfies these two constraints. First of all, small n divides p minus 1. And secondly, that p is larger than m. Then if you take your original orthogonal array to be the set of polynomials with coefficients in the prime field fp, whose constant term is 1 and whose degree is at most t, this also turns out to be a t-independent family. And the reason that we did this shifting and changed the simple polynomial construction of Bush slightly is the following, that this tau, which was defined to be the maximum number of big N's appearing among the rows of your orthogonal array, tau is now small. So you can show that there are at most t begins appearing among the rows of this orthogonal array. So there are a few of them, which is great, because using this previous result, we can now construct an orthogonal array over small n letters. So we can now construct an orthogonal array with small n levels and strength t with m columns, whose number of rows is, p to the at most order t. Okay. So here's the result that we have so far. It says that if you give me some prime, which is nice enough, p is larger than m, and it's also 1 mod n, then you can construct an orthogonal array, which is t-independent, and the level size is small n, and it also has at most p to the order t rows. Okay, so as you can see, the task that is left now is just finding a good enough prime p, which is hopefully small. And that's exactly what a Linux theorem gives us. So Linux theorem says that if you pick any positive integer k, then there's a fixed polynomial such that the first prime that is 1 mod k is at most a fixed polynomial in K. In fact, the degree of this polynomial has been shown to be at most 5.5 by a result of Hifron in 1990. So if you just plug these two facts together, you'll get a nice construction which works for any m and t. So you don't require n to be prime power anymore, and you'll get an orthogonal array with parameters m, n, and t, whose number of rows is some constant times mn to the order t. So the result we have so far is, as you can see, slightly suboptimal. It's missing the t in the denominator. And this is only actually suboptimal for a rather narrow range of parameters when t is always at most m, but this is suboptimal when t is at least m to the 0.999 if you do the algebra. And in any other case, it's going to be at least as good as what a polynomial in Rao's lower bound would be. But no problem. In order to get the tighter results, we need to sharpen our tools. And so what we're going to do is basically generalize this reassignment procedure that I told you about, and also use algebraic geometry codes instead of the simple polynomial construction to start with some orthogonal array. Okay, so I'll just be very brief about this and mention them in words, but we're going to generalize this reassignment process in two ways, and this is going to add flexibility towards how we're going to manipulate the entries. So previously, we used a fixed bad value begin and just looked at rows that had began and somehow modified those entries. We make two observations that are quite helpful. First, that you could take any other level in one through begin, not just begin, and that would also work as a bad value. Secondly, which is less obvious, is that you could assign a particular, a specific bad value for each column. So you could have m bad values b sub 1 through b sub m. And what this is going to get you is more flexibility in how to change the original orthogonal array. That being said, you also need a better original orthogonal array to start with. And that's going to come from algebraic geometry code. So instead of the simple polynomial thing that I showed you, we're going to work with them. And using them, we can avoid a very annoying trouble, which is great. We no longer need to require that m is less than p, which is quite helpful. Okay, and of course, I'm throwing away a whole bunch of details for the paper. But finally, we arrive at this result, which is that, we can get the t in the denominator and everything is deterministic. So we can construct orthogonal arrays with arbitrary parameters, m, n, and t, and with n not necessarily a prime power, such that the number of rows is a polynomial in the Rao lower bound. And also the whole thing can be constructed in a time polynomial in its size. Okay, that's all I have for the video. Thank you very much for watching.